Hello everyone, this is Sabita Sunkara. Welcome back to our Enterprise Data Engineer interview series. In the previous episode we discussed, that is 12th question is enterprise audit logging and monitoring, and 13th one is data lineage and data governance, and 14th one is enterprise data catalog and metadata management. Today we are going one step further. Our interview question is, what is data observability and how would you design an enterprise data observability framework for a modern data platform? Also, I am following up one more question here. How would you detect data freshness issues, volume anomalies, schema changes, distribution changes, and data quality problems before business users discover them? So this is an important senior data engineer question because they are very important in distinction. So a successful pipeline does not necessarily mean successful data. A pipeline can finish with a green status while still delivering incomplete, stale, or incorrect data. So that's the problem data observability is designed to solve. In the production scenario, let's talk a real world customer 360 scenario. Every morning, our customer 360 pipeline extracts data from multiple source systems. For example, core banking, CRM, third party APIs, and operational databases. Azure Data Factory starts the ingestion process. Then, the data is stored in Azure Data Lake. Databricks performs the transformations. Curated data is loaded into Snowflake. Finally, Power BI dashboards consume the data. Now imagine the pipeline runs successfully. Then ADF says success. Databricks job also completes successfully. Snowflake receives the data. Power BI refresh successfully. So, from a traditional monitoring perspective, everything looks fine. But the business team notices something strange. Yesterday, the customer 360 dashboard showed approximately 8 million customers. Today, it shows only 2.1 million. The pipeline has not failed. There is no technical exception, but the business data is wrong. This is the key problem. Traditional pipeline modeling tells us the job completed. Then the data observability asks, did the job produce healthy and trustworthy data? There could be several reasons. Maybe the source system delivered fewer records. Maybe an upstream file arrived late. Maybe schema changed. Or maybe a transformation filtered out too many records. Or maybe a business distribution changed unexpectedly. Maybe the data contains a sudden increases in nulls or duplicates. This is why we need data observability. So now let's look at how we implement this across an enterprise data platform. Our data platform might look like source systems, ingestion layer, data lake, processing, warehouse, consumption. So each and everything are set up in a platform. Then the important thing, the data observability should not sit only at the pipeline layer. It should provide visibility across the entire data lifecycle. So we can collect metrics from each layer. For ingestion layer, we can monitor file arrival, latency, pipeline execution, and failure information. Then at the data lake layer, we can monitor file count, file size, partition availability, and late arriving data. At the processing layer, we can monitor job status, record counts, processing time, and data quality metrics. At the warehouse layer, we can monitor load status, row counts, query performance, and data freshness. And at the consumption layer, we can monitor dataset refresh, report availability, and data product health. So all these signals from our data observability layer. So the purpose is to provide continuous visibility into the health of our data platform. Now let's discuss the 5 core dimensions we should monitor. These are extremely important in interviews. First one is freshness. Freshness answers, is the data arriving on time? Suppose the customer data set should be available by 2 am, but today it arrives at 8:30 am. The pipeline might technically complete successfully, but the business SLA has already been violated. So we have to monitor expected arrival time, actual arrival time, data timestamp, pipeline completion time, and latency between layers. If the freshness threshold is breached, we generate an alert. Then the second one is volume. So volume answers, did we receive approximately the amount of data we expected? Suppose our normally daily volume is 8 million records. Today we received 2.1 million. The pipeline may still process those 2.1 million records successfully, but that is a huge anomaly. We can implement thresholds such as expected volume 8 million, acceptable range 7.5 to 8.5 million. If the volume suddenly drops to 2 million, we can trigger an alert. Then the third one is schema. Schema monitoring answers, did the structure of the data change unexpectedly? For example, yesterday we had customer ID, customer name, customer status. Today, the source team adds customer type. Then a new column might be harmless. But what if customer ID changes when integer to string, or a column is removed, or a nullable field suddenly becomes mandatory? Those changes can break downstream systems or even worse, silently change the meaning of the data. Therefore, schema changes should be detected and evaluated before they impact downstream consumers. Then the fourth one is distribution. So distribution monitoring is a more advanced concept. It does not simply check whether the data exists. It checks whether the characteristics of the data have changed significantly. For example, normally active customers 82%, inactive customers 18%. But today, active customers 35% and inactive customers are 65%. The pipeline may succeed, but the row count may also look normal, but the distribution has changed dramatically. This could indicate a source system problem, a business rule change, a transformation defect, or a actual business event. So distribution monitoring helps detect problems that simple row count checks cannot identify. Then the fifth one is quality. Finally, we monitor the actual quality of the data. Example include null percentage, duplicate percentage, invalid values, referential integrity, business rule violations, and values outside expected ranges. So, for example, suppose normally only 0.1% of customer IDs are null. Today, suddenly 5.6% are null. That's a significant anomaly. So, the pipeline might still succeed technically, but the data product is no longer trustworthy. This is why data observability looks beyond infrastructure, health, and pipeline status. Now, let's look at what happens when observability detects a problem. It's not enough to detect an anomaly, we need an operational process to handle it. The first step is detect. Our observability framework continuously evaluates metrics. For example, volume dropped by 74%. Then the step 2, what it happened, alert. So the system generates an alert. The alert could be sent through email or Microsoft Teams notification or Slack. Then pager duty or an enterprise ITSM platform. Severity should depend on business impact. So a critical customer or regulatory dataset should have a different severity from a low priority development dataset. Then the third step is impact analysis. Now we need to understand what is affected. This is where our 13th question, lineage and capability becomes extremely valuable. We can trace affected table, downstream datasets, Power BI reports, dashboards, applications, and potentially business users. For example, one failed dataset might affect 5 downstream tables, 12 reports, and 150 dashboards. Now we understand the business impact, right? Then the fourth one is root cause analysis. Next, we determine why the problem occurred. We correlate pipeline logs, data quality metrics, lineage, source information, schema changes, and operational metadata. For example, we might discover the source file contained only 25% of the expected records. Now we know the issue originated upstream. Then the step 5 is resolution. Depending on the situation, we might reprocess the data or backfill missing records, then correct the transformation, or restore a previous version, or wait for the upstream source to recover. The important principle is don't blindly rerun everything. So use lineage and pipeline design to identify the affected stage and recovery safely. Then step 6 is verification and recovery. After fixing the problem, we don't immediately close the incident. We verify freshness is back with SLA or not, volume is normal or not, then qualify check pass or not, then downstream datasets are refreshed or not, then reports are corrected or not, then only do we close the incident and notify stakeholders. Okay, then after now we have to answer this question in interview. How would you design an enterprise data observability framework? So our answer would be, I would design data observability as a platform capability across the entire data lifecycle rather than limiting it to pipeline monitoring. First, we have to collect operational and data health metrics from ingestion, storage, processing, warehouse, and consumption layers. Then after, monitor key dimensions such as freshness, volume, schema, distribution, quality, lineage, SLA compliance, and performance. Then we have to define meaningful thresholds and baselines for critical data products. After that, anomaly detection, we have to use a combination of static threshold and the dynamic baseline, statistical methods, and where appropriate. Machine learning based detection also we need to use. When an anomaly is detected, the framework should automatically generate alerts based on severity and business criticality. So we have to integrate lineage to perform downstream impact analysis and correlate observability signals with pipeline logs and metadata to identify root causes. So for recovery, the platform should support controlled reprocessing, backfilling, and validation rather than the blindly rerunning complete pipelines. So finally, we have to track MTDT, that is mean time to detect, and MTTR, mean time to resolve, and continuously tune the monitoring rules to reduce false positives and improve reliability. Right? The objective is to move the organization from reactive troubleshooting to proactive data reliability. So there is one important point I would highlight in a senior interview. Data observability is not the same thing as data quality. Data quality asks, does this data satisfy our defined quality rules? Or data observability asks, can we continuously understand whether our data is healthy and detects unexpected behavior across the data lifecycle? So data quality is therefore one important signal inside a broader observability framework. Similarly, monitoring, lineage, catalog, observability. These capabilities complement each other. So, monitoring tells us whether systems and pipelines are running. Lineage tells us where data came from and what depends on it. Then, catalog helps us discover and understand data. Then, observability brings continuous health visibility across these layers. So, these are complement each other. These capabilities complement each other. Then the MTTD and MTTR means another concept that makes the answer more senior is operational measurement. So we should track MTTD, mean time to detect. How long does it take us to detect a data incident? If a problem occurs at 2 a.m. and we detect it at 2:05 a.m., that is MTTD is approximately 5 minutes. Then MTTR, mean time to resolve. This is how long does it take to restore healthy data. If we detect the issue at 2:05 a.m. and resolve it by 2:35 a.m., then MTTR is approximately 30 minutes. So a mature data engineering organization continuously tries to reduce both. So better observability reduces MTTD. So better pipeline architecture, lineage, automation, and recovery mechanism reduce MTTR. So let's summarize today's episode. A successful pipeline execution does not automatically mean successful data. So enterprise data observability provides continuous visibility into freshness, volume, schema, distribution, and quality, along with lineage, SLA, and operational signals. So it helps us detect problems early, understand their business impact, identify root causes, recover safely, and continuously improve the reliability of our data products. The most important mindset shift is don't wait for business users to discover bad data. Build a platform that detects the problem first. So that's what takes us for a reactive ETL support to proactive data engineer. Thank you for watching the Enterprise Data Engineer interview series. In the next episode, we will move from observability into another major enterprise architecture topic, that is modern lakehouse architecture. We will understand why organizations are moving toward lakehouse architectures, how data lake plus data warehouse plus data engineering plus BI plus machine learning come together, and how a senior data engineer would design it for production. Thank you.